Now we'll get started. So how are you guys doing today?
Pretty good.
Pretty all right?
How you doing?
Not too bad. Gonna teach some stuff today. So I put up the homework assignment. So the homework 4 is up. I waffled on how long to make it. There's only 4 problems, but one of them is doing the interface instabilities with surface tension. It's not super hard because it's all laid out in the book. You just have to do what happens in the book, and then add this piece of physics in it. It's all laid out in the problem, but it's kind of long. And the last problem is kind of long, and then the other 2 aren't so bad. So I don't think it's a super painful homework assignment, but anyway, it's due next Wednesday night. So I had said originally it'll be due next Tuesday, but I didn't get it out. So I figured giving you a homework that's due Monday on Thursday isn't cool. So today we're going to finish up interface instabilities and gene stability. Next Tuesday we'll do Rayleigh-Bernard convection and whatever else I haven't gotten to yet. And maybe I'll just ramble for an hour and it'll be funny. Hard to say. Next Thursday we'll go over homework 4 and we'll prep for the midterm. So we'll do both of those things in one day, and then the midterm will be on the following Tuesday, if that scans for everybody. I probably should have written that right there. Then I would have remembered that I said Tuesday. Yeah, Tuesday the 18th. That's what I wrote down there. Okay, so let us continue our talk about interface instabilities. So we went through, and I think I went through the actual dispersion relation kind of quick. So I'm going to spend another minute on it because some of the people were out, but now all the people were out the first time I did it are again out. So we'll go through it anyway. Because I think I didn't do this part very carefully because it was the end of class. So I'm going to say this stuff all again more carefully. Okay, so we start off with a 2-state system where we've got density and velocity in the upper state and density and velocity in the lower state, and these are all infinite in both directions because boundary conditions are a headache. We perturb it a little bit by a distance c, and we say that dc dt has got to equal the velocity in the z direction. And there's more to that by a lot. We expand this out, the full derivative. We turn this into the potential. Yeah.
Which way is z?
Oh, z is up. Thank you. Z is this way, and let's say x is this way. And y is out of the page. So Vz, which we knew is minus d phi dz. So we have to say this. That's important thing 1. Oh, important thing 1 is get an equation for phi. Important thing 2 is say that the interface moves with the fluid. Important thing 3 is to say that the pressure is constant across the interface. And then 4, you got to do it a little bit algebra. And then the Fourier modes. And then we get the dispersion relation. So kind of a lengthy process, but not super painful except for the first time you've done it. The first time you do it, it's kind of hard. Just because there's a couple of steps to go through. So that's why I'll give you the weekend to do it. So we go through all of this process, and then we get to the dispersion relation, and I'm going to pick up at the dispersion relation. So there, we found that omega over k equals rho u plus rho prime u prime over rho plus rho prime plus or minus the square root of all this stuff, g over k. G is the acceleration. We'll say that it's in this direction. G over k, rho minus rho prime over rho plus rho prime, minus rho prime u plus u minus u prime squared over rho plus rho prime squared. Square root of, maybe it's easier if I try to do it square root. Square root of all of this business. If I planned ahead a little better, that would have looked nicer. But so we have several different scenarios that we're gonna talk about. So the first scenario is where let's see, u equals u prime equals 0. In this case, this term goes away and this last term goes away, and we're left with omega over k equals plus or minus g over k, rho minus rho prime over rho plus rho prime, square root of that. So we have some subsets of this. So first, if rho is bigger than rho prime, then this is real, and omega is real. And we have a traveling wave solution. Remember this omega, what do these omega and k's do? Omega and k are in e to the I kx minus omega t. So if omega is real, then we get this sine and cosine kind of behavior. So if rho is bigger than rho prime, that means the dense fluid is on top of the light fluid and nothing's really moving. You flick it and a wave goes away from where you flick it at this speed. Now, second, if rho is less than rho prime, then this whole term is imaginary because this term is negative. So omega over k equals I times the square root of g over k times rho prime minus rho over rho plus rho prime. Where we just, let's put an absolute value here, just to be clear that we need the absolute value of that part. I switched the terms, but that's what I mean. But this I comes out, and that's the important bit. So then when we plug it into here, then we get a solution that looks like e to the I kx e to the plus omega t, or minus. But the minus isn't very interesting. That part just decays. It goes away exponentially. Things that go away exponentially fast, usually not particularly interesting. But the plus, where now we have e to the plus omega t, because remember we've got a plus and a minus on this side here, then this explodes. And one of the interesting things is that it explodes for every wave number. There are no wave numbers that make this term positive. There are no wave numbers that make this behave. Now for the homework, what you do is you add a surface tension that looks like T, which is just some number, times dc squared dx squared. So this is the second derivative of the interface. So that's the curvature of the interface. And the curvature is what gives you the surface tension. As it starts to bend, then those particles start to pull on each other, and they want to hang on to each other because there's cohesive bits in the fluid. So if you add this to the process, you get another term in the dispersion relation, and you get another term here that can be positive. So some wave numbers become positive, and some wave numbers are unstable. So you can see that adding surface tension makes the dispersion relation not imaginary all of the time. So this is what happens if you put a heavy fluid on top of a light fluid. And I did this with the bottle, and when I take the thing out, then everything is radially Taylor unstable and everything falls away. But when I have the card on the bottom of the bottle, it suppresses all of the unstable modes. 0 is not well defined here. K equals 0 is not well defined here. That doesn't travel at all. Okay, so remnants of my last work, my leftovers.
Dr. Collins?
Yeah.
I have a really quick question. What was the assumption that allowed you to say that v is equal to v prime, which is equal to 0?
I just make that assumption.
Okay.
So that's just a setup. I set up a problem like that.
Okay.
So that's just a way I can do that. So now if we assume that v is not equal, v and v prime are not 0, then we have omega over k, equals rho u prime. Let's just say that, let's say that u is 0, the fluid here in the lower part is 0 for a second. Then we're left with rho u over rho prime plus rho, plus or minus the square root of, also let's assume that rho is bigger than rho prime, so that the heavy fluid is on the bottom, because as we discussed, if we invert it, everything falls out. So we're left with g over k, rho minus rho prime over rho plus rho prime. So this is just the traveling wave part. So this is now if I've got an ocean and I'm the wind and I'm blowing across it. So I have a big velocity on the top of the across my surface. Minus rho prime u minus u prime, and we said that u is 0, so this is just u prime squared, over rho plus rho prime squared. So, how hard do I have to blow? Let's make a simpler thing. Let's just say I've got soup in a bowl and I'm having dinner with my in-laws and I'm blowing on this soup. How hard do I have to blow to get soup all over my father-in-law?
The thermal right has to be greater than.
Yeah. So this bit, so we just need to have this bit be less than 0. So that says that g over k, rho minus rho prime over rho plus rho prime. This is the bit that goes like the surface waves. Has got to be, sorry, I can't algebra, less than rho prime u prime squared over rho plus rho prime squared. Okay, so that's kind of gnarly, but whatever. So this says that this gives me a velocity. We can simplify this. I don't know if there's much point in simplifying that. We can solve this for the velocity for when this becomes negative, and when it becomes negative, then that's when my solution is unstable, because just imagine blowing on a fluid and you just get ripples, but if you blow really hard, it goes everywhere. That's what this says. So this says don't blow too hard. It's different from the wave breaking, because that actually happens. Let's talk. Sorry, I had an idea, and I think it's an interesting idea, and I can't tell if I know enough to talk about it. I think I will, just for a second. So, when we I did this once with an actual floor to get what gravity waves look like if there's a bottom to the ocean. And what we found was omega over k equals g times k times the hyperbolic tangent of, k times d. Now, if you're near the ocean, if you're near the beach, goodbye, chalk. You're there forever. What happens as the water gets shallower? D goes down and tan H goes down, so the wave speed goes down. Right? You follow that? So as D decreases, hyperbolic tangent decreases, my phase speed decreases as I'm going this way. Now, I've asked some oceanographers, and they say that this is kind of a dodge. because it's not really exactly how waves break. We don't really necessarily understand how nice curlers, like nice tubes form, but this is certainly a phenomenon that happens. So what happens is I have a wave that's going at a certain speed out here. Bloop, 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 wave, right? Not like anything interesting happening, just like going up and down, undulating. But then as it goes here, then all of a sudden that wave is going faster than the wave speed in that medium. That's a problem. So that's when waves turn over and break, because I have the top part is going faster than what the bottom part is going to allow it to do. So that's how waves break, because the dispersion relation changes with time. And then you can surf on that, which is one of the more entertaining things you can do with your time. Let's see. Oh, this is called, not this bit. This is called the Kelvin-Helmholtz. Instability. So Kelvin-Helmholtz is the shear instability. Oh, hang on one second. I might have something really cool. Sorry, I just remembered that I had a cool video that shows oh yeah, dope. Okay, this is gonna be fun. For some value of fun, where I make you do math all day. So, you know, my concept of me saying something is fun should be seen with some suspicion. We good? All right. Now let's point our camera at the TV, because this is the most so this is Kelvin-Helmholtz with so I don't remember which way the fluid is going, but it becomes apparent really quickly. So this shows the nonlinear breakup of Rayleigh-Taylor, or of Kelvin-Helmholtz. So what happens is we've got one side of the fluid is going in one direction, and the other side is going the other, and we've got this ripple, and it does this.
Looks like a fractal.
Yeah, that's not wrong. We'll talk about that later. And I lied. This is not Kelvin-Helmholtz instability. What instability is this? I forgot to write down who it was. Does anybody remember which one? This is heavy on top of light. You can tell because it's not going in that direction. It's going in this direction, right? The heavy stuff is, yeah, I can't actually, the file name is just some crap. This is Rayleigh-Taylor. This one over here is called the Rayleigh-Taylor instability. And I can't remember which Taylor this is, if it's the same as the Taylor series Taylor, or if it's GI Taylor. This is a really, really high resolution simulation. You can see all that gorgeous structure.
How long does this take to render?
I don't know, it's not mine. I've been showing this movie for a couple of years, so it's probably kind of old, so it probably took a couple hours, but it's a two-dimensional simulation, so you could fit a pretty big one on a pretty small computer. One of the things you can see, watch over here on the right-hand side. Watch these guys. See how these two things are spinning and merging? Just watch this vorticity merge together. Now we've got this vortex. I didn't know this was going to make a vortex like this. Because I watched it, I knew, because I could see what was going to happen. Now I've got this really big vortex. What does this look like to you? Or this guy here? Oh yeah, that one there. What does that look like to you?
Like a hurricane?
Yeah, it looks like a hurricane, doesn't it? You know why it looks like a hurricane? Because it's this very similar physics. So we'll talk about turbulence in a couple of weeks. One of the things about turbulence is it is structure cascades to smaller scales. When you shake it up, when you shake up fluids, you start with something big and you shred it into smaller scales. Now, if you're in 2 dimensions, like we are here, or like the surface of the Gulf or the the Mid-Atlantic, if you're in a basically 2-dimensional simulation, you're missing a degree of freedom. So the helicity, which is like the vorticity, is goes to larger scale. So you get vortices that merge together and get bigger and bigger and bigger because you have vortices of all the same sign that all merge together and get larger and larger and larger. And that's where tornadoes and hurricanes come from.
So
Yeah.
the lighter fluid was on top for this?
Yeah.
So why is the white in the center and not the black is on the outside? Very end.
Well, let's watch.
I thought you said the white was heavier.
White's heavier. White's on top. I retract whatever I said before. White is heavier. White's on top. And so this has a floor of some kind. I'm not sure what they did with the boundary condition here. It's not periodic. Sorry, I'm stalling because I can't answer your question yet. But now I can.
No, that makes more sense.
Now I understand.
Denser. It's sort of like how in planets where all the dense stuff goes to the center.
Yes, partially, but also, where are we at? Yeah, let's write this up. So here, this is bigger. You could see it. The phase speed goes like 1 over K sorry, I'm brain farting. I was going to explain something, but then it didn't work the way it does in my head. I did something wrong. I'm getting there, I promise. So omega over K goes like G over K. So what grows first, large K or small K? So which has a larger growth rate? So they actually, I see what I did wrong. Omega is the thing. So let's get another. Oh right, I hate this board. I forgot. I like every other board. Okay, so our dispersion relation here, what I wrote was omega over K equals the square root of G over K times rho minus rho prime over rho plus rho prime. That's in the right order, isn't it? Yeah. So if this is negative, if the interior is negative, then the outside is imaginary. And what we want to think about is omega, not omega over K. That's the phase speed. We just want to think about omega because that's going to give us what the growth rate is. Omega is K times G over K square root. So this is just goes like a square root of K on the outside. And then I should invest in more chalk. Or just ask Kevin if he's got some. So omega equals the square root of K G rho minus rho over rho plus rho. So now I'm righted. I looked at it and I was getting it totally wrong, and I was going to say something that was totally back-asswards. But okay, look at this now. So if this is negative, then omega equals I times the square root of K times this thing, whatever that is. So what goes first? Which has a larger growth rate, big K or little k?
Little k.
So the growth rate is going to be omega. So big K means bigger growth rate here. So because the growth goes like e to the omega t now. So if omega goes like square root of k, then if square root of k is large, then the growth rate is larger. Does that make sense? Now, big K is little size. So that means that small structures grow first. Everybody follow that? What happens first? Small structures grow first. Watch the little tiny bumps on the perturbations are what start to grow first, and then followed by bigger modes. So a small mode doesn't stay a small mode very long because it gets eaten by a bigger mode. And so we have this cascade of things going from small scale structures to bigger and bigger and bigger scale structures. So to answer your question, why is all the white in the middle? Because what you're left with is just one big mode, and everything else is kind of mixed. Everything else has gotten washed out. All of the other instabilities have grown and mixed. All you're left with is the one big mode that's left over. So you just kind of get one central blob that wants to collapse. Does that make sense? So the growth rate depends on the size of the structure, and for Rayleigh-Taylor, small things grow first, and then big things take over. For Kelvin-Helmholtz, where's my K dependence on this? So if I'm blowing with a fixed U, then as K gets bigger, I guess the unstable mode changes. Yeah, depending on how you blow, different modes are unstable. Does that make sense? So the unstable mode depends on how you're blowing, but also the size. So if I blow harder, I can smaller things are unstable. Cool. Okay, does that make sense? What do you feel like? Yeah.
I'm still a little confused about why the smaller structures grow first.
Oh yeah.
For the Rayleigh-Taylor.
Yeah. Because so we have our dispersion relation is omega over k equals g over k times delta rho over average rho. Like that. So the growth rate is I times omega, because the thing that we're plugging it into goes like e to the I omega t times e to the I k x. There's a minus sign there, but that doesn't matter too much. So this is what our wave looks like. I mean, I add those together and I get kx plus kx minus omega t. But I separate them because this one's going to become real. So, but I just want omega, not omega over k. So I get the k to the other side, and I'm left with omega is just equal to square root of k times the square root of g delta rho over average rho. So this is a parameter of the system that stays the same because you're not changing the density of the fluids. But k is the wave number. Now k is inverse wavelength. So when I have sine kx, k and x multiply to give you 1, or something that's dimensionless. So k has dimensions of 1 over length. So when I look at this, I say, well, what's going to grow first? Things with large omega are going to grow first. So what do I have to do to make omega large? I look at the right-hand side, and I see that that's when I make k large. So large k means large omega. Large k is small structure. Good?
I think I understood everything except for the first part of that.
Which part?
Saying that omega grows the most when that whole expression is largest.
Oh, well, I mean, this is just a parameter. So if this is big, then this is big, then this grows fastest.
Oh, okay.
Yeah. So I just put a bigger number right here, and then the t gets to use that bigger number, so it grows faster.
Okay.
This will show up again, so if it still doesn't make sense in a minute, let me know.
All right.
So that was Rayleigh-Taylor. Where's my thing? It's over there. Here, and they have a thing like this, And there was the first year I did this, there's a device like this. I'm sure going to pull up another movie. There's a device like this in the end of the GFDI. Yeah.
Is that what happened with the water, but really fast?
Yeah, this is what happens with the water, but it goes really quick. And you can so this is a simulation, and it's beautiful. Making a fluid this beautiful requires complicated things because getting an unperturbed surface is really pretty tricky. So one thing you can do is have a bucket of water and then a piece of metal, and then heavier stuff like salt water, and then you pull the piece of metal out. But then you kick up a bunch of Kelvin-Helmholtz instabilities because you've got all this velocity, so you swirl everything up. But it works, and you can do a Rayleigh-Taylor that way. My favorite Rayleigh-Taylor... Oh, do I have it? I'm trying to think if I can get the picture. Let me see. I'm just going to spend... Oh, no internet. Yeah, never mind. Okay. My favorite experimental setup of the Rayleigh-Taylor is use the biggest laser in the world to explode a little piece of plastic. I'll tell you about that one later. But one of the coolest ways that they can do something like this in the lab at University of Arizona, they have this, I think it's 4 stories tall chamber, and they've set up a bottle or a container of fluid with salt water on the bottom and normal water on the top, and then they put rockets on the side and they shoot it at the ground as fast as they fucking can. And then they do this. And that's the best way to get these really beautiful mushroom rolls. So these beautiful mushroom rolls are characteristic of the Rayleigh-Taylor. And you can see these kinds of things all over the place if you start looking for them. So what the linearization that we did just tells you about how fast this grows. All of this little small scale structure all comes from the nonlinear stuff that we threw out. And we don't have a good way to describe it, but it's often described as bubbles and spikes. So you get spikes of things that go down and bubbles that go up. And you see all of this swirling, That swirling is Kelvin-Helmholtz. I'll show you Kelvin-Helmholtz in a second. Oh, what's this thing? So they have an apparatus just like this one in GFDI. So what's going on here is you've got a really long tube, and it's got salt water in the bottom and fresh water in the top, and they're going to tip it, which, because of gravity, causes a shear. The heavy fluid is going to start to go down, and the light fluid is going to start to go up. But in that shear layer, it's going to form Kelvin-Helmholtz, and you'll see the Kelvin-Helmholtz that we describe start to grow very quickly, and then it goes nonlinear very quickly.
This experiment to look at the Kelvin-Helmholtz instability
I did not realize there was talking
between 2 layers of fluid begins with a clear layer of fresh water
Where
on top
is...
of a denser red-dyed layer of salty water in a long horizontal tank.
Oh, yeah, cool. I don't need this guy talking. I just said all those things. So this is the setup where you got to do this really carefully, because as soon as it's mixed, and this experiment's over, because water and salt water are perfectly miscible, so they will just mix like crazy. So it's the setup of this project is really careful, so they slowly fill it up with salt water, and this takes like an hour, I think, to set it up. And then they go. And it gets cool in a second. There it goes.
Oh.
Group. And then it mixes. So here's the shear, and you can see the little wiggles start to grow, but they don't take very long before they're fully nonlinear. So there you go, and now it's nonlinear, and now it's curly, and now it's mixing. You see that roll over? Have you ever guys been in an airplane and had it turbulent? this is what's happening. Waves are breaking like ocean waves. Let me see if I got that movie. I got this whole directory of movies of fluid instabilities that we're just going to go through. Here's another one. Oh, this is another code. Oh, that's just their sky. My sky is better. This is another code. Where's my stupid mouse? This is a moving mesh code, so you can see the little boxes all roll around each other, because this code is smart. The last code I don't think did, but this code does. The parcels move with the fluid, which is useful when you're doing something like this. But you can see that linear phase doesn't last very long before now it rolls up, and now this is something that we can't describe. Our description of C does not roll over onto itself. It has to be a function. This rolls over onto itself because that's what nature gets to do. So these Kelvin-Helmholtz rolls, and I like this. I like the way they visualize this because it feels like a mosaic from like ancient Greece or something. So you see this roll up. This is really carefully controlled so that they are only exciting one mode of the instability. They excite one mode and one mode grows up. Whereas in the last one, they seeded a whole bunch of little modes, so you get a whole lot of little modes that grew. This one, only one mode is present initially, so that's the only thing that grows. So that's why these are all the same size.
Other comments?
Yeah.
For clarification, what exactly do you mean when you say a mode?
That's a great question. So K is what I mean. But we've got a bunch of Ks. So I could set up this way I'm not standing right in front of the video. So if I've got a wave, this wave has one wave number K, right? So this is one mode. But on top of this, I can add other stuff. So I can add a higher frequency mode, like this. And now I have two modes. Now I have a high frequency mode on top of a low frequency mode. And I could add another one. So I could add little frequencies. Now I have a whole bunch of modes. I've got some big ones and I've got some little ones, and so I've got a bunch of different frequencies. So a mode is just one particular, it's the content at one particular size. That makes sense? So this one, all the stuff is the same size, so they seed it initially just with this one perturbation, which you can't actually see in the initial conditions because they perturb it in, I'm going to go out and guess they perturb the velocity. So I'm not exactly sure what they perturb, but you can see that only one wavelength is present. There's only one size structure because that's how they built the simulation. Oh, here is one. Here's a Rayleigh-Taylor where they started with this lab was, I took a summer school at Cambridge on fluid dynamics, and their fluid dynamics lab is like Disneyland for nerds who want to get wet. It's the coolest. They have these huge tables that spin around and all kinds of cool stuff. It's a lot like what they have going on in here, but it's got Cambridge money. So this is another one of those Rayleigh-Taylor instabilities where they have a bunch of salt water on top of a bunch of fresh water, and they've got a board in between, and they pull the board out, and then the Rayleigh-Taylor develops. I guess we get some 2000s vintage. No, we'll just let it go because it's actually so. And this is looking from the bottom. So this is actually upside down. Because it's more satisfying to watch. It's kind of unsettling if you watch it all caving in. And I don't remember what else they do. Oh, okay. So now instead of just two interfaces, they have some stacks, which will look a little differently. And you can see the Kelvin-Helmholtz instability kicked up as the thing rolls past, and then that seeds Rayleigh-Taylor instability, which grows these bubbles. That one didn't mix everything, did it? Because this one, they have it set up so that it doesn't go as far, it doesn't drop as far. I was going to say something else. Now I can't remember. Anyway. So they sped this up by a factor of 2. Why did this one go slow? Well, let's look at our growth rate. Did I erase it again? No, here it is. Let's look at our growth rate. Here, I'll make the growth rate over here. K goes upstairs for the growth rate. So omega is, if this is negative, then omega is going to be our growth rate. And it's going to be dependent on the density difference. So if I make the density difference very large, like air and water, then the growth rate's really fast. If I make the density difference small, like salt water and fresh water, then it goes a lot slower. So these movies, I think, were all real time. So that's really how fast that develops. Whereas with the water bottle experiment, that would happen much faster because the density difference is large. Okay. What other cool movie do I have showing instabilities? Yeah.
Are the small modes the same as like the bigger modes? Do they have the same curve to them?
A small mode is curved more. A big mode is curved like that, and a small mode is going to be curved like that. And the curvature is going to go like k squared. Why is the curvature going to go like k squared? What is k? This is a more sophisticated question than I think anybody's ready for. The answer that I'm looking for. K is a derivative. Remember?
Isn't k the frequency?
Yeah. But remember how I got k into this mix in the first place? As I turned all my derivatives into multiplies by k. All my derivatives with x are all multiplies by k. Remember doing that? Because I have e to the I kx, and then I take a derivative with respect to x, and that pulls down an I k. E to the I kx. So differentiation, when you're in Fourier space, just turns into multiplication by k. So if I want to know what the curvature of one of these modes is, I just need to know what the second derivative of that wave is, and that's just k squared. Does that make sense? Anyway, that's neither here nor there. This is another Rayleigh-Taylor. Oh, I still got to do genes. Oh, that's just a GIF. It's not an interesting GIF. Or GIF, if you're like that. This is a single mode of Rayleigh-Taylor. So you can see that it starts off with just one wave, and then that grows. The heavy stuff falls, the light stuff rises. And you can see along the side, you have shear. So we have Kelvin-Helmholtz picking up on the side. So all of the secondary instability is called the Kelvin-Helmholtz, the shear instability. And the primary instability is the Rayleigh-Taylor instability. Let's see.
Whoa.
Yeah, this one. I don't see it like this very often in Florida. But check that out. I would see the clouds doing this, like this perfectly rolled up when I lived in New Mexico, because one side of my commute was at 7,000 feet. The other side of my commute was at 7,000 feet. And in between them was the Rio Grande at 5,000 feet. So there's this huge valley of really perfectly still air with mountains on the other side. So the air would come over the mountains and just gently blow across this lake of air that's just sitting there and curl up the clouds into these. So I saw the clouds do this, I don't know, half a dozen times in the 2 years I was living there. It's kind of magnificent. So this is all real nature. It's not just oh, here is another one. This is a slightly different instability called Meyer Meshkov. All instabilities are named after two people for some reason. Maybe this is Vishniac instability. I lied. Vishniac instability is only named after one person. So what's going on here? This is the Crab Nebula. So you've got a wind that's at a pulsar that's down off the center, and it's blowing low-density hot gas into the interstellar medium. That low-density hot gas is running into the higher-density cold gas of the stuff that it lives in, and it does stuff that's just like Rayleigh-Taylor. It forms these spikes of fingers and stuff. And then, oh, this is that one again. That's all my cool movies. Okay, now I'm gonna do genes. And I ran it a little longer than I intended to. But now I only got 20 minutes. So, gene stability is a lot like deriving sound waves. It's a really very similar process. So I'm not going to go through it in the same kind of, with the same kind of carefulness. And my notes are similarly much sparser than they were for sound waves. So the basic idea is there are a lot of jokes. So James Jeans was a scientist. And we're going to talk about the gene's length and the gene's mass and gene stability. And Thanksgiving comes up, and then we can talk about how bad our genes fit because we put on all of our genes mass. These jokes are way funnier to me than they are to anybody else. So gene stability is when you have hydrodynamics plus gravity. And the question is, what's the biggest thing you can support with pressure? Because as things get bigger, the gravity gets bigger, but the pressure doesn't change. The pressure is just the local quantity. So if I have a thing that's this big, it's got a little bit of gravity and some pressure. If I have a thing that's this big, it's got the same pressure, but a lot more gravity. I'm being super glib there, so careful with that interpretation. So what we're going to ask is, what's the biggest thing that we can support before it collapses? So let's see. Let me strategize for a second. There's two different ways that I can do this. There's several ways that I can do this. And I'm going to give you the cheap and dirty one first because you read the long one in the book. So the first one says, okay, blob of stuff. I fucking caught it. It fell out of my hand and then I caught it. I'm a wizard. Okay, so I've got some blob of gas that has some size L and some sound speed C sound and some density rho. So decided I'm going to do it this way. Where'd my notes go? Did I leave them upstairs? It's hilarious. Derp. Okay, I may screw up a pi in this. Okay. How fast does this collapse? I just have a sphere of stuff. Okay, let's change gears. Forget about Hydra for a second. Let's just talk about, I have a sphere with constant density and radius r. How long does this take to collapse if we ignore the pressure? We can sort this out because a sphere of uniform density, you might have learned this in mech, but you will when you take mech if you haven't done it yet. If I have a sphere of uniform density, thanks, man. We're gonna get it. Mathematically and gravitationally, that is equivalent to a point source with mass m equals 4/3 pi rho r cubed, the mass of the total sphere. So if I'm sitting at the edge of a big cloud of gas, or the sun, or the earth, or whatever, and by some miracle, I could stay put and the whole earth could get squished down to a point, the gravity that I feel would be the same. Doesn't matter because it's symmetric, because of the symmetry of the stuff. Okay, so that's one thing. So we're going to say I got a point here that's at some distance r from the center. Let's just let it collapse. Make sense? So what does that look like in real life? So if this is going to orbit this point, and this is all going to bring up the celestial mechanics stuff that you did in mech, or will do in mech, but I'm not actually going to use any of that. So if I'm in orbit around this, then my orbit looks like this. But if I squish my orbit so that its eccentricity is 1, and I'm just going, here's my total mass, here's where I start, I can squish my orbit so I just fall straight at the star and then orbit back again. And I would just fall straight down and hook right around the surface of the star and then shoot right back out again. Does that make sense? So what does Kepler say about how long it takes to orbit a star? So Kepler says, and this is the thing that I forgot to write down that I always screw up a pi, T orbit equals pi over g times m plus m square root of that times the radius to the 3/2. Am I missing a 2 in there?
2 pi.
Ah. Nice. I needed a 2 pi missing. So this is what Kepler says. So this says that the time it takes to orbit is 2 pi over the mass times the semi-major axis to the 3/2. So this is one of Kepler's laws. You can derive this from basic celestial mechanics. I'm not going to. So this is the time to go from this point all the way around. What I need is the time to go from this point to the center. That's only half of that. So T free fall is T orbit over 2. So that's where my 2 goes. And R, well, okay, I'm sorry. Not R, A. A is the semi-major axis.
That's the horizontal, like, radius, so to speak, here?
Yeah. Yeah, so A is sorry, brain farting. A is the semi-major axis. So this is my ellipse. My planet is at one focus, is at one end of the ellipse. So my semi-major axis, if I start off at R, my semi-major axis, A, is R over 2. That makes sense? So I have a sphere. How did I do this? I have a sphere. I squish it all to a point, and I'm going to orbit this on a straight line that goes straight to the center. So A is R over 2. So T free fall, there's a way simpler derivation of this that is only a little bit wrong that I'm going to make you do for homework. So T free fall is going to be T orbit over 2, so this 2 goes away. And this A will replace by R over 2. So this is just pi over G big M square root. I'm going to call little m 0. I don't have any mass. Times R over 2 to the 3 halves. M is just 3 pi, is 4/3 pi rho r cubed. So I plug that in here, and then I'm done. I've got pi over G times 4/3 pi rho r cubed square root r 3 halves over 2 to the 3 halves. It's kind of hairy. So you finish up that algebra, and the r's cancel, and you're left with T free fall equals 3 pi. Oh, the 3 comes from here, and the 32 comes from this 2 over 32 G rho. This is the time it takes for a sphere to collapse if there's no pressure. You can work this out with dimensions by just using the dimensions of G and rho. This is how you're going to do it in the homework. It's way faster. It's not as hard. You can just say, what are the dimensions of time if all I have is G and rho? And you get 1 over square root of G rho. So just using the dimensions gets you most of the way there. 3 pi over 32, square root of 3 pi over 32 is like a half. So not off by very far. So yeah, this is how long it takes for a sphere to collapse. How long does it take if my sphere is of length L and I have a sound speed c sound? How long does it take for a pressure disturbance to go across this object?
The sound speed divided by the length.
Try again with, think about the units. You're on the right track. I'm just going to wait for you to do it.
Would it be the length divided by the sound speed?
Sound speed is in meters per second.
That's what I meant, yeah.
Length is in meters. So it's length divided by c. Sorry to put you on the spot. I realized after I did that that was a terrible idea. So length divided by the sound speed. Okay. I think that you're just done now. Let me change colors. I'm going to upgrade to blue. Length divided by the sound speed. And I have to do that every time I sit. Every time I sit and do this, I'm like, okay, it's going to be c sound times the length. And then I keep going because that's not right, but that's what my brain always wants to do. So it's the length divided by the sound speed. So this is equal to, so if t cross is larger than t free fall, is it going to collapse or is it going to be supported? If the crossing time is longer than the free fall time. So we've got these two competing forces. Gravity is going to make it collapse in one time scale. Pressure waves will wash out that density over density on another time scale. If the crossing time, if it takes longer for a sound wave to go from this side to this side and wash out the density than it takes for the whole thing to collapse, then you're in trouble. So then you're unstable. So this implies instability. So we have L over C sound. If this is greater than 3 pi over, let's just call it 1 over G rho, square root of that, then the length is equal to the sound speed over G times rho, square root of that. So this is the gene's length. It's about 32 inches if you're a 5 foot tall American man. So this is the size of a structure. This is the biggest thing that pressure can support before it collapses. And this is related to the temperature, because remember we sorted out that the sound speed is related to the temperature. Now, when I ask you to do it again in the homework, don't use this. This is a short derivation that I can do in 6 minutes. The longer derivation picks up a couple extra factors of pi. So the long derivation, I got 15 minutes. I can do the long derivation. Let's do the long derivation of that. This sheet is just so I get all the pi's right. Because I love pi. Okay, let's do the same thing, but we'll start from Navier-Stokes. Let's start with Euler. dv dt plus v dot grad v, and we'll throw that term out, is minus 1 over rho grad p minus grad big phi. Big phi is gravity. Remember, del squared big phi equals 4 pi g rho. This is the gravitational force law. If you haven't seen it this way, that's okay. I'm telling it to you now. This is how we do it. So this is the thing that relates gravitational potential and density. So you can see where this comes from. This is called Poisson's equation because it shows up a lot. There's a lot of things that look like this, where you've got del squared of something is something else. You can see this. I'm not going to go through the proof because I don't care too much. But basically, force is minus grad big phi. And big phi is the integral of rho over r minus r prime, rho of r prime, dr prime. There's a g. So this is what the gravitational potential is. This is just add up 1 over r. It's mass divided by potential. You do a little bit of algebra, and you take the gradient of this and then take the gradient of this again, and then you wind up with this. There's a couple of things that turn into delta functions for weird reasons. But this form of gravity is the same as f equals grad phi, and phi equals the integral over density. I don't need to worry about that. I literally never think about the potential as an integral over density. You want to see a really fast way to solve this equation? If I boost to Fourier space, this becomes k squared phi hat equals 4 pi g rho hat. And then phi is just 4 pi g rho hat times k hat, or times k to the minus 2. So you can get your gravitational potential just by working in Fourier space and multiplying by k to the minus 2. Then Fourier transform back, and you get your potential. I don't need any of that right now. So what are we going to do? We're going to go up here. We're going to take this. We're going to have d rho dt plus div rho v equals 0. And we'll do the same stunts that we did before, where we say we're going to linearize around rho naught, p naught, v naught equals 0. We're going to say that grad p equals c squared grad rho. And we're going to linearize everybody. And so when we linearize everything, we're left with dv1 dt. This goes away because linear, over minus 1 over rho naught, minus c squared over rho naught grad rho 1. Should be familiar to everybody. Now I've got another thing, minus grad phi 1. Oh, I've got a potential field. Uh-oh. Phi equals phi naught equals constant. This bit here that I forgot to say originally, and now I'm saying it, is called the gene swindle, because you're not allowed to actually do this. But we're going to do it anyway, because fixing it up is a headache. But you can fix it up and make it rigorous. I'm just not going to. So grad phi 1, this is just again the force. Remember, F equals grad phi. So this is my gravitational force. This is my pressure term. This is V. This is V is equal to d rho dt equals minus grad rho naught v1. That's just what we get from the linearization, rho 1. Because everybody comfortable with me having gotten here with and is familiar with these linearizations, because we've done them a couple of times now, but I'm happy to go through it again if anybody wants to see it again. So I just do the same cross differentiation of both of these things. So I'm going to cross differentiate this with a nabla. This gets a square and this gets a square, and I'm going to cross time differentiate with this, and this gets a square and this gets a dt. And then I subtract, and this term cancels this term. I got to multiply through by a rho naught in there. And then I add, and I'm left with d squared dt squared of rho 1 minus c squared of d squared dx squared rho 1, that's just the nabla again, equals minus del squared phi 1. Oh, times rho naught. Ah, what is del squared phi 1? It's 4 pi g rho 1. Cool. Equals rho naught times 4 pi g rho 1. Okay, so this is the same thing that we found with sound waves, except now we have this extra term at the end.
Wait, shouldn't it be a negative on the...
This one?
No.
Yeah, probably. I was doing this kind of quick, so I might have dropped something. So we do the same stunt with the Fourier analysis. And here, stop me if this isn't obvious that I'm writing this down. This turns into a minus omega squared minus c squared plus c squared k squared equals rho naught 4 pi g. I think that's all I need, right? Yeah.
The
rho 1 went away when I got rid of all the other rho 1. So this rho 1 here gets differentiated, and I'm left with k squared and a rho 1. Here I get an omega squared and a rho 1, and the rho 1, and this rho 1 all cancel. Like 80% sure that I didn't screw anything up. Okay, so now we rewrite this, and we get that omega squared equals c squared times k squared minus what we'll call kj squared. And kj is rho naught times 4 pi g over c sound squared. Or the gene's length is 1 over the gene's number. Maybe there's a 2 pi here. I'm really kind of sloppy with that 2 pi sometimes. Because, okay, we plug it into a cosine kx. And this goes around every 2 pi, regardless of what I stick in here, right? The period of cosine is 2 pi. So a lot of times people want a 2 pi there. So there's a 2 pi that's there. Your entire career as a physicist is tracking down a 2 pi that you lost somewhere. So this 2 pi is because just from the geometry. So then the gene's length is going to equal to c sound squared over rho naught g. I missed a square root in the last one somehow.
I think, yeah, kj squared to kj.
There you go. That's why it's squared. Thank you. C squared over rho naught g. This is the same thing that I got in the last board, way easier, right? It's just the gene's length is just c. That's just the sound speed over square root of g rho. And then there's some pi's and stuff. Pi to the 47.9. I don't remember what pi is. But I don't really care. Well, I should care. But it's getting late on time. And the important bit is we go through the same nonlinear or same linearization of the equations, and we get something that looks basically the same thing that we got from just looking at the dimensions, which is pretty fun. Yeah, the only thing that I'm missing actually is 2 pi on the bottom. So that's gene stability, and now we can form a gene's mass. The gene's mass is going to be 4/3 pi rho naught times the gene's length cubed. So what does the gene's mass tell you? So I've got a cloud of gas in outer space, or on Earth, but it doesn't really matter on Earth. I've got a cloud of gas in outer space, and it's got some density, and it's got some temperature. Sound speed is temperature, right? Sound speed squared is just the temperature, and then there's some constants in there. But so this tells us what the temperature is, and this tells us what the gas is. So if I have a big cloud of gas and it's very cold, it will make a bunch of little stars. If it's very hot, it will make a couple big stars. So if I have 1,000 solar mass cloud, and its gene's mass is 1 solar mass, then it'll make 1,000 1 solar mass stars. If I have 1,000 solar mass cloud and the gene's mass is 100 solar masses, then I'll make 10. So it depends on how much pressure there is to support the cloud. I think I'm going to stop there. Does anybody have any questions on any of this? Let's see. We'll have office hours on Friday. Just show up if I forget to announce it again at 4 o'clock if that works for you guys. And then again on Monday at 4 o'clock for anybody who wants to make it that. And let me know if those times don't work for you. And have a good weekend.
Question out of curiosity, just because of the form of this, is there any relation at all between astrophysics with things like foreshadowings?
Oh yeah, it's awesome.
Any correlations with the gene's length in particular? I mean, I guess you can solve this for like G and then plug that into.
Yeah, you can get a gene's density. So the sound speed is really the important key, because when that gets very high, then
I'm pretty sure
I've not finished one.
Oh, well, 1.3, whatever. I'm pretty
they
sure I
don't
got the
have
logic
this
for
plasma,
one
and that's more of a problem.
Even though it's difficult to study and work on your writing.
Yeah, there's
Well, I was like